what we're going to talk about today, they're not that difficult. I hate to say they're kind of simple in terms of arithmetic and algebra. They're probably one of the simplest stuff we can do, but you want to get introduced to the idea of a vector. Okay? Now what you're seeing here is a vector. All right. Now you might say, what is a vector? Is it an arrow? Well, we represent it with an arrow. But a vector, by definition, is really this. Okay. It is an object. You say, what do you mean? It's an arrow? It's an arrow. All right. It's an arrow that has two things. It represents two things. Something called magnitude. Now, if you say, what in the world is a magnitude? A magnitude is the length of the vector. And so you go, oh, how long that is? Yeah, every vector has a length. You go, oh, is that how long it is? Yeah. Every vector has a length. We call it magnitude. But it also is pointing in a particular direction, ladies and gentlemen. And you go, really? How do you think they measure the direction? Well, remember that thing called a horizontal, by the way? Remember this imaginary line with a horizontal? That's how they're going to eventually measure the direction. So I want to remind you guys a few things here. This object, this arrow, has both a magnitude, a length, and it has a direction, and we represent it by an arrow. And it's really something used extensively in science. Vectors. It's a foundational kind of thing. So you'll see this in a lot of science courses. A lot of science courses are based on these vectors. That's why we want to talk about them. Okay? So at least introduce them to you guys. All right, a vector. Have you guys ever seen these before by any chance? You might have vectors. No, good. Then we got some work to do. All righty. Okay, so here's what I want to start with you guys with a vector. Here's the kind of the starting point, right? Back in geometry, all you needed was 2 points, okay, to draw like a line to some degree, or really a line segment in geometry. But a line segment, it's related, but a line segment doesn't have that arrow. Okay? There's no pointed direction for a line segment from geometry. So this is really related to that idea in geometry of a line segment. 2 points A and B. But they use, in geometry, the notation they would use is something like this. Okay? So this is kind of like, that's the notation for a line segment. And in geometry, they go, oh, okay. Here's your point A. Here's your point B. That's a line segment. But you say, no, they put AB with an arrow. Well, that's not a line segment. That's a vector because we use these arrows. And sometimes we let a single letter represent that. Now, like geometry, or maybe not like geometry, but the order in which you read these letters is important. Meaning you have the A as you read left to right. You have the what? The A value, and then you have the what? The B value. So you say, well, why is that significant? Well, A is called an initial point. Remember, this isn't a plane. It's a point. Bless you. So A is an initial point. B is a what? Terminal point. You got the initial point, you got the terminal point. Okay? So that's kind of what I'm saying here as well. We call A the initial point, B the terminal point, with a magnitude represented. Oh, here's some notation here. Okay? Remember the idea of the word magnitude. The word magnitude represents length, the length of the vector. So you might say, well, they represent this as the absolute value of v. Yes. This is kind of the notation as well. You can say, oh, but v is the same thing that you're seeing here. This is an arrow, sorry. So when you see this notation, automatically that's just the length, how long it is. Okay, so it's going to be kind of a simple idea, believe it or not. We're going to put some things together here, okay? So remember, like in algebra and geometry, you're familiar with points, right? Plotting points. So you can plot the initial point and the terminal point. Essentially, you can draw the vector. Just make sure the arrow goes to the terminal point. So this is just plotting points in like beginning algebra. Okay, so all right, we can plot points A and B, and we can draw the vector with those coordinate values. And you go, well, what do you mean coordinates? Well, remember, you have both an x coordinate and a y coordinate in that xy plane. Is that right? You guys remember from beginning algebra and the x coordinate and the y coordinate? All right. Well, you go, okay, what do I do then? Well, you got something called an initial point and the terminal point. So you put 1 for our initial point. You put 2 for the terminal point. So we can draw points A and B, or plot them, and you draw this arrow now. And that's the arrow. And what you see here, ladies and gentlemen, is what we call a vector. So, for example, now, you go, okay, what do you mean? Here's A and B. Here's going to be my initial point. So I put 1 there, and I put 2. So I have my initial point, terminal point. Notice the address is there, right? 1, 2, the initial point, and then 6, 5, the terminal point. Okay, just by plotting these points there. Here's the vector. All right, you guys okay with that? So you can draw these vectors given coordinates like this. So it goes back to like beginning algebra. All right. So now you say, okay, since this is the vector, right? Generally speaking, remember that thing we want to find? You say, what do you mean? The magnitude and the length? So what can happen very simply as you draw that vector, notice in general what this means here. We can create from that drawing, generally speaking, a right triangle, right? So you can say, well, how do I do that? Well, you're not given this point, but we can draw a right triangle here. And then all the information we need from like geometry, we can apply. Okay? And then now you have A, you have B, you have C, you have angle theta. So in some sense, we're just using geometry. Does that make some sense to you guys? What do you guys remember from geometry? You go, well, we have what? I want to let you guys know. This A value down here, A is called the horizontal component, that length. Do you guys know how you measure length by any chance? Okay, here's where x1 would be. That's the location here. So I'm going to label this here. Here's x1. And this location is x2. How do you measure length horizontally? Do you guys know? I'm going to show it to you guys what I call the ruler. It's the right value. Oops. I guess I'm going to use the letter A because I don't want to use L twice. So this length here for A is found by taking the right value we called x2 and the left value we call x1. So if you said, is that x2 minus x1? Yes, this is the horizontal component. And then we have this version, which is called the vertical component. So this is going to be the y1 coordinate and the y2 coordinate. So I want you guys to see here how you measure length vertically. You guys may not realize it, but it's top minus what? Bottom. Okay, you guys okay with that? The top minus the bottom is how you get what we call a vertical length. So that's y2 minus what? y1 here. So you might say, is that how they got that vertical component here they're calling? Yes. So you have two things, A and B. And that's kind of like ABC, the sides of a right triangle. And you got C, ladies and gentlemen. What is C? C is the hypotenuse of a right triangle. So this is using language from what? Geometry. But we're linking geometry and algebra here. All right, so that's kind of really what's going on. You're seeing the algebra and the geometry. So fundamental ideas, but so important. Remember, horizontal distance is the right value minus the left value. Vertical distance is the top value minus the bottom value. And that's where they get these definitions, I should say, or formulas for A and B. That's going to be really important for us. Okay, it's going to be helpful for us to find the length. Because now, with Pythagorean theorem, what do you guys know? C squared equals A squared plus B squared. Okay? Not only that, from geometry, what do we know? The definition of tangent of theta is B over A. All right? Tangent theta is B over A. And that's why they kind of changed the notation for you guys. Okay, you guys okay with that? So far, so good? Not too bad? All right, now I'm going to give you another definition of the vector. Yeah. I'm going to give you the definition of what we call the component form of a vector. V equals AB. So essentially, your book defines it this way, right? The book is going to say, hey, guess what? We want the component form of a vector. This is really what the book tells you is the component form. Okay? It is that A value, comma, B value. But you might say, well, where did they get these A and B values? Well, it's from what I just defined for you guys here. It's the horizontal component and the vertical component. That's how we start to algebraically describe a vector, right? Well, you want to call this the algebra or geometry definition. It's really both. Okay, geometry comes from the right triangle. The algebra comes from the plotting points. So sometimes we're saying, boy, algebra and geometry are really linked together. And they are. Okay, so let's look at an example again, that first example that we're talking about here, right? You say, okay, A is 1, 2, B is 6, 5. They want us to determine the vector V. Well, what do they mean by determine that? Let's get the component form. Okay, so you're going to take the x values. What's the difference? You're going to take the y values. What is the difference? So remember, you have to really know those numbers. Here's my first point. Here's my second point. So you might say, okay, x1 is 1. Is that right? x2 is 6. Take a look. This is where it's coming from. So if we say, what's the difference between x2 and x1? Well, that's 6 minus 1, which is what? Which is 5. So this is why we say A is 5. So when we start to write this vector here, instead of the A value, right, we're going to say, oh, we know what you are. You are 5. We're going to need the B value now. All right, so you go, well, how do we get the B value? Well, y1 is right here. It's the y value in the first point. So y1 is going to be the number what? 2, right here. And then y2, because you say this is an x coordinate, y coordinate, x coordinate, y coordinate. So what's the value of y2? Well, y2 is going to be 5. So that difference, y2 minus y1, you say, what's that going to be? 5 minus 2. And so this is going to be the value 3. Okay? So what you guys are looking at is what we call the component form of a vector. All right. So A down here is 5. B here is 3. This is the length. This is what we first had to do. So a big part of what you have to do is you're just looking at this here. So this is how we describe that vector V formally. In component form. This is an extremely important definition. Component form. Now, you might say, well, what's coming up next? Remember, what are the two things you care about with a vector? This is the graph, by the way. We know what it looks like. We're going to care about what? The length and the what? Direction. With the component form, we can find the length and we can find the what? The direction. You might say, how do I find the length? Well, isn't that C? That's a right triangle. Is that right? So from the right triangle, well, what do we know? What do we write down? Well, we know C squared is A squared plus B squared. That's by Pythagorean theorem. C squared is going to be what? 5 squared plus 3 squared. Is that true? And maybe we should just put some of this work over up here. Yeah. Yep. Well, the hypotenuse is a length. So the hypotenuse is a length here. So then C is a square root now of what? 5 squared plus 3 squared. So you say, what am I finding, Mr. Judge? I'm finding the length here by using the Pythagorean theorem. That is called the C value, right? By Pythagorean theorem. You have a right triangle down here. The length of our vector then is numerical. It's not always a nice whole number. That's 25 plus what? 9. Do you guys know what this is? Isn't that the square root of 34? That's the square root of 34. So the square root of 34, if I approximate to the nearest tenths, I already have the calculator there. You guys see that there? That's going to be 5.8 then. So notation-wise, you can say we found the length of this vector v to be approximately 5.8. That's the meaning of what you guys see right in here. Yeah. No, that's a very good question here. You got a very good question. You might say, Mr. Judge, whatever happened to the idea of plus or minus? Because you went out and you used some algebra. Isn't C plus or minus? And I'll say, yeah, the answer is yes, it's plus or minus. But you might say, then why didn't you do that? Well, what does plus or minus mean? It means you have two solutions. It means one solution is positive, and it means the other solution is what? Negative. The problem here is this. If they ever ask you to find distance, ladies and gentlemen, distance is never negative. You have to throw out the negative value. See, by algebra, yes, you got two numbers, plus or minus. There's two there, plus or minus. But distance is always positive. So that's why you're going to see here, the absolute value of v is about approximately 5.8 to the nearest tenths. That's the approximate length of your vector, and it's a positive number. All right, now, ladies and gentlemen, you might say, okay, that's all fine, but how do I find the direction that this vector is pointing? Well, what they mean by direction, they mean you have really here what? There's a horizontal here. There's length out. It's a horizontal. You're going to try to find theta. That's what they mean. They want that standard angle. So you go, okay, what do I use? We use what? Here's what we say. Let's see if you guys know this. You guys remember? Tangent theta is opposite over what? Adjacent. Is that true? You're finding, yes, finding the direction, which is the angle theta. That's your direction. Theta is a direction, right? We drew that. That's a hypotenuse. This is the same kind of thing that you did before with everything. You have that horizontal. That's what they mean by what direction. What is theta? So opposite is going to be what? 3. Adjacent is 5. Now, this isn't a very nice, I should say, this is not a special triangle situation, is it? So the reason, and you had a good question, do we get to use a calculator? Yeah, because now I can get theta by doing what? The inverse tangent of 3/5 by using your what? Calculator. And, you know, this is set to degrees. And so I have it in this format here. So if we go out to the nearest degree, what does that mean? What does theta have to be? What is theta? Should we be consistent even with our colors? Did you guys see that in the calculator I have here? Theta is what? Theta is 31 degrees, ladies and gentlemen. So what you see here in that worksheet there, and I don't think, let me go back here. Let me show you here. I didn't show this where you get it. You go, Mr. Judge, where do I get it? Go to my worksheets, whatever, this video library. It's still a work in progress. I apologize. There's your vectors. Come on, internet. The wireless in the basement is a little problematic. There is the worksheet. Okay, just to kind of go back there and let you guys know the worksheet that I made for this stuff. And double check. This is the summary, ladies and gentlemen, of all the important details associated with this vector V here. You got the component form. Of the vector. You have its magnitude. What does magnitude mean? Length. It's approximated to the tenths. And you have a way to describe the direction. It's 31 degrees. So that's kind of some of the fundamentals they want you guys to be able to understand and know about any vector. Can you graph it? Get the component form? What's the magnitude? What's the direction? What do you guys think? Is that easy peasy lemon squeezy? I told you, it's not that bad. It's based on arithmetic and some geometry, algebra, trig, really. But this is going to be where you start in a lot of ways with the world of vectors. All right, and so now, ladies and gentlemen, as you guys can see here, you know, what I've done, what did I do? Yeah, I made kind of a worksheet on this stuff here to try to get started on those kind of things. You guys know what I mean? So maybe one day Barnes & Noble will buy my notes. Maybe they'll buy the website. Maybe Elon Musk will buy the website. And I can, I don't know, go to Maui or something. So here we go. They're going to give you A and B again, where this is going to be our initial point here. Okay? So call that initial point, terminal point. Don't forget, here's my x coordinate, here's my y coordinate. Here's my x coordinate, here's my y coordinate, ladies and gentlemen. Okay, so let's get the component form. Well, they say sketch. Sketch, what do they mean by that? Let's plot A. A is at 0, -2. So let's find that location, okay? Where is 0, -2? Do you guys know what that means? That's just below down here at -2. There's your location for A. Because here's your address. Where is B? B is at 4, 2. So you're going to go to the right 1, 2, 3, 4 units. You're going to go up 2 units. So here's location B. Okay? So when you draw the vector, just draw an arrow. Okay, so remember, this is my what? This is the initial point, and this is the terminal point. There's your vector. There's a sketch of the vector. Okay. So how do you think we're going to get the component form here? Right? You're going to use the definition. So vector v in component form is going to be what? x2 minus x1. That's the horizontal component. y2 minus y1. That's the vertical component. So you may have to, and I used to do this myself, looking at the points, I used to have to write down what x1 is and what x2 is. What is the value of x1? Here's my x coordinates. It's the first numbers, right? So x1 is the first x value. That is 0. Do you guys agree with that? What is x2? 4. Okay. Now, what do you guys need? You need the y values. Okay. What is y1? -2. What is y2, ladies and gentlemen? Isn't that what? +2. So double check that we're doing everything okay. So we need to now do what? We got to take 4 minus 0 right up in here. And the other one is going to be what? 2 minus a -2. Be careful there. People, this is where people make a mistake because they don't always, they think that, oh, there's a negative sign. This is minus a negative. y1 is -2. So this is minus a minus. Okay? So what do you get for vector v now? What's this going to be? What's 4 minus 0? Isn't that 4? What's 2 minus a minus? Isn't that be 2 plus? This is 2 plus 2, which will be what? 4. So, ladies and gentlemen, here's your vector, 4, 4. So, if you want, you can say, did we label that A and B? Yes, we did. A, there it is, and then what? B. So we have found the component form of the vector v. So, I mean, if you wanted, you can say, is that going to give me this right triangle? Sure. Yeah. Yeah. Well, this is the sketch of the vector in blue right here. So essentially, they're asking for this. They want to know, can you draw that? Because that actually has a lot of uses, applications of it. So can you draw that arrow? Yeah, it's right there. They're going to want to know, now that you know the component form, so here's the sketch there. You're looking at everything there, the blue vector component form. They want to know the length. They want to know the direction. So you might say, well, how do I find the length of this? Well, what do you guys think? How do you find the length? Sometimes they'll write it this way. The length of the vector is the square root of that what? A squared plus B squared. So the length of this vector is the square root of what? 4 squared plus 4 squared. 16 plus 16. Square root of 32. Now, you can really simplify this. Square root of 16 square root of 2, so that the length of this vector is really going to be 4 square root of 2 symbolically. Okay? So you might even see the answer symbolic, 4 square root of 2. Now, what is that numerically? Well, 4 times the square root of 2, which is 5 point what? 7. And there it is. Tangent theta, by definition, how did they define tangent theta? Right? Once you get your A and B value, remember the definition of tangent theta? It's B over A, which is 4 over 4. So you're going to have geometry and trig because, well, it's going to be, in this case, simpler. What's tangent theta going to be here now? Isn't that going to be 1? What does that mean theta has to be? Isn't theta pi over 4, which is 45 degrees? So your angle is pi over 4, which is 45 degrees. There it is. So the direction that this vector is pointing that you guys sketched here, that's a 45-degree angle, just so you know. I'm doing all this detail for you guys because it's important. But to sketch the vector is just in blue. Okay, so you know the length. What was that length? 5.7, was it? Don't remember. 5.7? Was that the length we just got? Okay. So those are the details of this, ladies and gentlemen. So I guess in some ways, you know, they're just finding the component form, the angle and direction. let's go down to maybe number, I don't know, let's try to do this one here, number 5 maybe, I don't know. I don't know, 5 or 6. I don't know which one you want to do. We'll do the first and the last one. It doesn't matter, but. Okay. The initial point, put 1 for initial. Put 2 for terminal. X coordinates, Y coordinate, X coordinate, Y coordinate. So if you're going to get the component form by definition, write this down as what? X1 is 3. X2 is 5. Is that true? Double check. So then that A value is the difference. X2 minus X1, which will be 5 minus 3. What is the value of A? 2. Y1 is what number? -5. Y2 is what? -4. So that B value is going to be what? -4 minus a -5. What is this? -4 plus 5, which is going to be +1. So B is 1. So we didn't graph this. We will, but we know the component form. Definition is AB. Okay. 2, 1. This is the component form of a vector. But it's not the graph, but we're going to graph it. But I want you guys to see the arithmetic first, these definitions. So you might say, okay, what does this really look like again? Where's the point 3, -5? 3, we go to the right, 1, 2, 3. -5, you go down 1, 2, 3, 4, and 5 right here. Okay, so this is that address 3, -5. This is my initial point here. Terminal point is 5, -4. So you go, okay, where's 5, -4 at? Well, we're going to go to the right. 1, 2, 3, 4, 5. And then go down 1, 2, 3, 4. There we go. Now, maybe you don't need to list the addresses if it starts to get a little cumbersome. But now connect your what? Connect your points with an arrow. That is the vector V they're talking about. All right, you guys okay with that? And you also have the what? Component form. Now, that's important. Can you guys tell me what's the magnitude? Isn't that square root of 2 squared plus 1 squared? Is that square root of 5? So the magnitude of this vector is what? Square root of 5. Take a look at the calculator. Second, this is square root what? 5, ladies and gentlemen, and you now get what? It's about 2.2. Approximately. Anyway. Okay, how do we get the angle? What's the definition again, right? Get the angle, magnitude and direction. So what is this going to be? Do you guys remember? Is it B over A, right? Isn't this tangent theta is what? 1/2? Is that the definition? Do you guys remember? I don't remember. Nope. Magnitude is the what? Is the length. Theta is the direction. Okay. So inverse tangent of 1/2, is that right? So this is going to be, if we go out to the nearest degree, isn't this going to be what? 27 degrees? Is that true? Actually, no. There's no special triangle. This is 27-degree angle, you know. So, and it brings up a remark that you guys want to be aware of here. It brings up a remark, which is extremely important. That when you deal with inverse tangent, you got to take a look at the direction, okay, of the arrow here. Right? So that's a quadrant 1. If you said, hey, what do you mean direction? Well, that's kind of like quadrant 1. If I can draw your x-axis and your y-axis, this is quadrant 1. You want to make sure that makes sense. It's a quadrant 1 angle, 27 degrees. But there is no special, you're not always going to have a special triangle, especially with vectors. That's why you get to use your calculator. But the idea is to actually have a what? The idea, ladies and gentlemen, is to, be aware of that inverse tangent. And we did work with this stuff even with calculators. Let me give you guys a couple of definitions here. Okay? I'm going to give you guys a couple of definitions that are going to be very useful for us. We'll call that some vector notes. Okay. Give you a definition. This is going to be very important in your lives about vectors. Definition of a unit vector. And they say this is kind of the notation U. And they'll write it as U1, comma, U2. You have the horizontal and vertical components. Definition of a unit vector represented this way. That is a vector with magnitude equal to 1. This is what we call a unit vector. Okay, so if you have the length of your vector being 1, well then you know what? We call it a unit vector. Here's an example, or I'm going to give you guys a fact here. We have some very, very, very famous unit vectors. In this course, we'll have 2 very famous. They're so famous, they have their own letter. This is called the I vector. Okay? And the J vector. They're famous. They're in math and science. I vector, J vector. Some of the most famous vectors you'll ever meet. These are the very famous unit vectors. Now you say, why are they unit vectors and why are they so famous? We're going to see why. First of all, notice, what's the length of vector I? By definition, it is 1 squared plus what? 0 squared. Is that true? So do your arithmetic. 1 squared is 1. 0 squared is 0. 1 plus 0 is 1. What's the square root of 1? Isn't that 1? So what do you know about this vector? It's a what? Unit vector. Because the word unit means 1. So any vector with length 1 is called a unit vector. So I is a unit vector. That's what you really want to notice. J is also a unit vector. Because why? It has a length of what? 1. So the 2 famous unit vectors in trig are both the I and J vectors. And these are actually kind of known as a basis vectors in other courses. Because they form a basis. You might say, what's the basis? Notice this. If you're to graph those vectors here, let's see if I have a graph here. Come on. Let's see if I have, do I have a Cartesian coordinate? I think I do. If you were to graph those kind of vectors, we want to see what they look like. I and J vectors. There we go. Zero, 1. We said, how do I plot 0, 1? Well, I mean, this is kind of small. X is 0, Y is 1. And I guess we're using purple. There is what they're talking about. This is the I vector. The J vector, 0, 1, is right up here. So these are known as basis vectors. They form the basis of the X coordinate system and the Y coordinate system. This is why they're known as basis vectors here. And it's in 2 dimensions. Here's your I and J vector. These are basis vectors of the coordinate system. Okay, now you say, why do you care about these vectors, I and J? Well, because we can actually perform arithmetic properties really with vectors. There are properties of vectors that we're going to study, vector properties. It might even be in my sheet. You say, what do you mean? Yeah, there's some properties here. So we're going to start to see the properties. We have the first property is known as vector addition. Right? So now you're given two vectors, v and w. We're going to see what it means to add vectors. Okay? We have something called scalar multiplication of vectors. It's why you multiply a vector by a scalar. Scalar is a number. Let me show you guys the definition of it. And we have vector subtraction. We can show you where that comes from, because we have negative scalars. And then we could do some arithmetic with this stuff. So there's some properties about vector addition here. So anyway, ladies and gentlemen, what I'm going to say to you guys is this. Even though you don't have the answers to those, I want you guys to finish off these other examples like 2, 3, 4, 5. Okay? So this is going to be, you say, where do I find that? Well, that's back in my website. To start with those, do some vector addition here. Get to the fun. Now that we did all the chores, the administrative chores, let's get to what's fun about this class. The work, the fun part, the stuff that makes sense. Okay, this is why I actually enjoy mathematics, if you guys want to know the truth. when I grew up in chaos and insanity and things that didn't make any sense. And the one thing that made me feel better was the fact that math was consistent. That was gold in my world. And so, we can see how this works. So I want to share with you guys some important vector information in our lives. Like V, remember, this is a component form. And here's W. We got two vectors now, another component form. This is how they define them. We have a way to algebraically add vectors. Okay? Now you say, well, how? Well, you see the X components, and maybe I should go back, and I apologize for using these colors. I'm going to try to use the colors that we used yesterday, right? So you got A1, and you got what? A2. Do you guys see these X components, the first components? So how we can algebraically do this is we add the X components here. So that's the X components, the horizontal components. And then we're going to add the corresponding what? Y components. Vector addition. Okay, so it's a very simple process. It's based on arithmetic. But let me actually share with you guys really the real definition of vector addition here, okay? Because we care about vector addition. We can perform vector addition in what we call freehand. And this is really how they define it, if you guys want to know. You can move these vectors around. You see, what they say here is if you take the first vector, vector V here, right? You have the initial point for vector V and the terminal point for vector V. So here's the real freehand version of how you can add vectors. Freehand, meaning vectors can move around. We just move them around by freehand. Okay, so vector V now, the first vector in blue, is graphed. And then you go, but what about this vector W? What do you mean you could move it? Yeah, we can move any vector around. As long as we keep the length and as long as we keep the direction, we can move them. So what you do for vector W, the second vector, notice you align the initial point with the terminal point for the second vector. Now, this is automatically its terminal point here, okay? But this is the freehand version of how you can add vectors, okay? This is graphically. This is algebraically. This is the algebra or the arithmetic of vector addition. You can add them. But graphically, this is what it looks like. Now, you might say, okay, I did this work. I described it in the notes right here, okay, to create what's called that resultant. But what happens if I connect the initial point of the first vector with the terminal point of the second vector? I get a new vector. This is the initial point of the first vector right here. The terminal point for the second vector, if I do this, let's get this out of the way. I get what we call the vector sum, and that vector sum is extremely important in a lot of ways. This is called the resultant vector. It's almost like saying, is that the result when you take a vector what? Sum. And the answer is yes, that's the result. So you care about the resultant vector. Okay, because vectors in physical science represent things like force. So you could get a resultant force. Okay, they can also represent like distance and direction. Well, you get a resultant, distance and direction there. Okay, so this is kind of a lot of great work comes from vectors. We also have another concept with vectors called scalar multiplication here. So here's the resultant vector, how we can add graphically and algebraically. And then we have another operation called scalar multiplication. So you say, what's a scalar? Do you guys know what a scalar is? A scalar is a fancy way of saying number. C is a scalar. It's just a number. Okay? And so you say, well, what happens with that C? Well, if I take C times some vector V here, right? A scalar multiplied to a vector. All you do is you distribute, ladies and gentlemen, that number C to both components. So you have the first component, that X component, orange, Y component, green. So you take that C to both. So this is called scalar multiplication. Now, if you said, what is the physical meaning of this in terms of a picture? Okay. Consider the freehand description. So if I said, here's vector V, okay, here's my original vector. We can take the scalar number, which is a number, of 1/2, and we can multiply that 1/2 by V. So we're saying, what is half V? Well, what that does, it's a half the distance of V. In other words, it shrinks the size. So it shrinks the size by 1/2. It doesn't change the direction. It just shrinks the length. Okay, you guys understand? That constant number makes it smaller. That's an important thing. That's kind of a big deal. And you go, what if the number was like 2? What if the scalar was 2? Does that mean I can double my vector? Yes. Double the vector. So I get 2V now. We're going to double the vector. And that just doubles the length. It doesn't change direction. Okay, you guys okay with that? So I just want to let you guys know why physically those numbers are there. That just makes it either longer or shorter. Okay? Now, what can happen is that constant C can be negative. This is when the constant is positive. Okay, you got a constant. What happens when the constant's negative? Well, like in this example, the constant is negative. It switches your direction. So the negative number switches direction. And if you said, well, what if it's a negative 1/3? Well, it just switches the direction and it actually shrinks the vector V. So just the negative number switches direction. Negative 1/3 of that, it just switches direction and it's actually 1/3 of the length. Finally, over here, you got -3 times that V. So, ladies and gentlemen, it switches direction in the opposite direction, the negative number, and it makes it longer by 3 times. So I want you guys to see graphically as well the effect of a constant times a vector. I want you to also note, okay, this is going to be important in the world of vectors. You say, what happens if C is 0 here? Well, if C is 0, okay, we can still distribute that 0. That's 0 times A, 0 times B, and you happen to get the vector 0, 0. So I want you guys to understand this. This is kind of like a very trivial thing, but it's really not so trivial. You do have something called the zero vector. And that's really, the components are both zero. That's a zero vector. So when your components are both zero, you say, well, how long is that vector? 0, right? And what's the direction? Well, it's kind of undefined. So the length of this vector is 0, but there's no direction. It's the zero vector. It's not even, it's kind of like a funny default, okay? But it's algebraically important for us. Because now we can actually define for you guys what is known as vector subtraction. And you might say, well, how do we get vector subtraction? Well, let me go back to the notes, because I want to prove it to you guys. Okay? Bless you. Vector, bless you. Vector subtraction. If you have vector, and I think, I'm not sure how do we define it? Let's go back. A1, okay, A1 and with subscripts. So I want you guys to see the algebra here. Here's vector V in component form. Here's vector W in component form. So notice subtraction here is written really as the addition of a negative. Now that's -1 times W. A1, B1 plus -1, A2, B2. So notice the arithmetic. Okay? So what you can do is you can distribute that -1. A1, B1 plus -A2, -B2. And now you can perform vector addition. A1 minus A2, B1 minus B2. So ladies and gentlemen, I know you say, well, that's addition of a negative. Yep. Addition of a negative is known as, by the way, subtraction. So the reason you might see this definition for vector subtraction here, ladies and gentlemen, is because this is where it came from. They use those properties of vector addition with scalar multiplication. So I want to kind of share that with you guys where this comes from. So now you say, well, what is this? A1 minus A2, B1 minus B2. Okay, so we're going to share these with you. In fact, let's give you guys another fact here. So yesterday, I left you guys with the I and J vectors. I can define vector AB this way. This is component form. And so that vector AB can be written as AI plus BJ. And in some ways, this is the preferred way to write a vector. This is the IJ form. This is the preference of writing a vector. We prefer this. Okay, so you might say, why is this the preference? because it makes vector arithmetic easier. Okay, we prefer this because we can perform vector arithmetic. That's why. So I guess we should say this is the fact here. Okay, this is the real fact, and I can show you guys. I can prove to you where it comes from because, you know, we're gonna want to use this, so you guys know. So here we go. You say, where does this come from? Well, here's the vector we start with. I can write this vector this way because of vector addition. Okay, you guys okay with that? Because of vector addition, I can write it this way. A0 plus 0b, because we just add the components. I can even factor out an A and factor out the B by some algebra. Okay? And then I can say, did you guys recognize from your notes yesterday, what do we call vector 1, 0, that unit vector? That one had a name. Do you guys remember the name of this vector? What's the name of that vector? We call that the I vector. Do you guys remember that? And this is called the what? The J vector. Those are those special unit vectors I gave you guys. So we can say this is vector AI plus vector BJ there. Yeah, there we go. So this is the proof behind what we call the IJ form of the vector. That's the proof of this. So this is kind of your preferred way to write a vector in some ways. Okay, so notice the components here, right? A and B, those are the components. What was A? Don't forget, A is called the horizontal component. B is your what? Vertical component. So you got these components. Yeah.
So what you just proved to us was just the formula. This is more condensed than it was.
Yeah, it's actually, I'm going to show you guys why you care. It helps you perform the arithmetic a lot easier. You know, like you said, we're going to show you guys why. You say, Mr. Judge, why do we like this? Why is it preferred? Because they're both really good ways to describe the vector. But you say, why do you prefer the IJ form? In other words, in science, you're going to look at the IJ form. So in the science courses, they look a lot about the IJ. You go, why do they care about the IJ form? Well, there's a lot more to it, but let me show you guys what we said. You can do vector arithmetic. But in this example now, okay, you might say, well, what does this stuff mean? I don't think I have any space here, but we'll try to do that, right? Let's take a look at this. How are they defining these vectors, right? I can now define vector V as 2I minus 3J. Do you guys agree with that? You say why? I'm going to illustrate why you care. Okay? So here's why we care. Now, what is vector W? How do we define vector W? Say, is that 1 times I plus 5 times J? Yes. All right, you guys okay with that? So notice the first question. What do they want you to do here? They want you to determine the sum. Isn't that called the resultant, right? This is known as the resultant. So when you guys move forward in science course, you go, what's the resultant? That's the vector sum. All right. Just think of that as a resultant, as the result when you add. So you might say, well, how do I do this? Well, let me just see if I can do it this way here, okay? Let me copy everything I wrote down. If you remember beginning algebra, you go, what do I mean by beginning algebra? You take vector V, you add it with vector W. What does this have to do with beginning algebra? Do you guys remember combining like terms? Anybody know what I'm talking about? How did you combine like terms? Here's 2I minus 3J. I guess I have to write everything down again. All right. Plus 1I plus 5J. So the reason we care is because we just combine what? Like terms. You're combining like, do you guys remember how to combine like terms? Right? So what terms are like? Good. Let's do this. 2I plus 1I. What does that give you? 3I. Good. And then what's the other like terms? Do you guys remember? It's negative 3J plus 5J. What does that give you? Plus 2 what? J. There you go. You guys are done. So the IJ form is the preference to write a vector because it enables you to do vector arithmetic a lot easier. They just tap it. You just tap into people's past algebra skills. And it's beginning algebra, meaning combining like terms. This, ladies and gentlemen, is the vector sum. So you guys know. And this is called the resultant vector. So you got the resultant. So if you say, okay, but what does that sheet want me to do as well? Oh, where is it? No, it's not under vectors. It's under vectors. What? Oh, it is. I'm on the sheet. Oh. What does number 2 say? Can we take the difference? Yes. You might say, how do I do the difference now? Okay. Well, you say, here's vector V minus, can you subtract vectors? Yes. 2I minus 3J. Okay? Minus, put that in parentheses. If you want, go back to beginning algebra. 1I plus 5J. And you go, oh, is this how we subtract? Yes. Distribute. Do you guys remember? You drop the parentheses here, the first one. You distribute that negative sign. And then you combine what? Like terms. What's 2i minus I? Isn't that 1i? Good. You guys okay with that? Okay. What's negative 3j minus 5j? What's this? That's negative 8j. Do you guys know what you just did? Vector what? Subtraction. Nice. Easy peasy, lemon squeezy. So that's kind of why you like the IJ form, because it goes back to beginning algebra. You don't have to learn a whole other. It makes things easier to do the arithmetic, I think. That's why it's preferred. And then you go, what about this situation, right? You go, oh, 3v? How do I get 3v? Well, that's scalar multiplication. 3v. Okay. So here's 3v. You guys okay with that? Take 3. What is v? Oh, we have it here. Sorry. It's 2i right here. 2i minus 3j. All right. Sorry. So do you remember beginning algebra? What do you do with this? You what? You distribute. You guys okay with that? What do you get now? 6i minus 9, what? J. Do you guys see how it makes the arithmetic easier? Because you go back to just the distributive property. You go, what do you mean the distributive property? Yeah, you guys remember? I know people like this. Do you guys know what I discovered? People like that purple algebra. They like these formulas. They even like it with letters. I like it with shapes, but people like the letters. What do you guys think? Does that give you a visual of what you're doing a lot better? Maybe it does. All right, what's the other one here? Negative 4 what? W. Negative 4W. What is W? I plus what? 5J. So we can say I plus what? 5J. So negative 4, let's distribute I, and then negative times a positive, what does that give you? Negative 20 what? J. Okay, easy peasy lemon squeezy. All right, let me ask you guys this question here. How do you do number 5 when they say, what's 3v minus 4w? 3v minus 4w, isn't that based on arithmetic? 3v minus 4w. Well, you can do it this way. You can take 3, and what was v? 2i minus 3j. Yeah, we did. All you can do, what you can do is just add these two if you wanted. Right? You can just add these two. Don't you get 2I, what, minus 29J? Do you guys know what I'm saying? But what if they gave you this from the beginning, right? You go, I don't even know, I didn't do the prior work. So if they gave this to you from the beginning, where maybe you didn't even do the prior work on this, right? Maybe that's what happened. Minus 4 times W. What is W? 1I plus 5J, also known as I plus 5J. Okay, so if they gave you this from the beginning and you didn't even do the prior arithmetic, this is what I'm going to assume. So if they did that, and you go, oh my God, why do they want me to? This is, again, beginning algebra. You go, what is that? 6I minus what? 9J minus 4I plus 20J. So if they started this off, here we go. Six I minus 4I is what? 2I. Did we make a mistake? I plus. Oh, that's minus. Yeah, we did. This is a minus. Okay. So what's negative 9J minus 20J? That's negative what? 29J. So ladies and gentlemen, you're performing what's called vector arithmetic. You could do arithmetic with vectors. And nice. All righty. Yeah, let's go back. All right. Now, here's what I'm going to say to you guys. By the way, I'm going to give you guys a note here. You go back and you look at the, I guess we are in the notes. We are in vectors. You go back and you say to me, oh, Mr. Judge, what do they want me to do? Find the magnitude of the following vectors. How do you guys think you could do find the magnitude? It's very simple. Like the first one, what was the vector sum? Isn't that 3I plus 2J? Right? Can I erase all of this here? It's in our notes. Yeah, let's erase it. We already have that. It's in our notes. Hey, we could go back and rewatch the video if we wanted, right? Okay. Do you have the difference? Okay, so how about this? How do we take the magnitude of V and W? Do you guys know? At the square root of 3 squared plus what? Square root of 2 squared? Is that true? You say, how do we know? Because we have the components. 3 squared. 2 squared. What's 9 plus 4? Is that the square root of 13? So based on yesterday, yes, if you get a vector sum, that's another vector. You could get the magnitude of that vector and you could get the direction. So if I said this to you guys, all right, What's the direction of this resultant vector? Here's the magnitude. What's the magnitude again? Isn't that the length? How about the direction? Do you guys remember the direction? How do we get, what do we set tangent theta equal to? Isn't that a over b? Isn't that going to be, is that 2 over 3 or 3 over 2? What was it? Wasn't it b over a? Yeah. Yes. Well, theta is going to give us the direction of that vector. Right? So we're going to try to find theta. Because remember what we had yesterday. This was the b value over the what? The a value. Is that true? Do you guys remember? Where you say a is not 0. And so here's the thing. This is probably not going to be a special triangle, which means we're going to have to wake up our what? TI. So I want you guys to know they can ask you for magnitude and direction just like before. Right? So remember this. How do I find? This is not a special triangle. You're not going to get a special triangle here. Theta is the inverse tangent of 2/3. Didn't we have homework in how to find that? Do you guys remember? How to use the calculator with this? I think we had homework with that. Yep. It's the inverse tangent of 2/3. So you say second inverse tangent 2 divided by 3. And what is this in terms of degrees? If we go to whole degrees, you guys know what that is? I'm talking whole number. So the 3, this is 33, but the digit to the right is a 6. What's that going to give you? 34 degrees? Now let's see. Does that make sense to say it's 34 degrees? What do you guys think? Theta is the direction of this vector. Does that make it in some sort of sense? Why do I say, does that make sense? Do you guys know? What quadrant is 34 degrees in? Good. What quadrant is the vector in? Do you guys know what quadrant is this vector? This is at 3, what? 2. So here's 3, and here's what? 2. I know you're hard to see, but maybe I can move that down. But I want to verify, ladies and gentlemen, that this is a quadrant 1 vector. Because your calculator is very limited. It doesn't give you the answers to every angle. You guys know that, right? It's quadrant 1 vector. Yeah. If they ask you. But typically, to let you guys know, like in science classes, yeah, like you can take a science class where they do that. They want you to sketch the resultant. This is called the resultant. They want you to find the magnitude and the direction and the sketch of the resultant. These have a lot of applications. Vectors have a lot of physical applications. I really wish that we had a lot more time to go over a lot of the vector applications, but you always have to choose. Do you want to go to applications for law of sines, cosines, and right triangles, or do you want to wait to vectors? I used to, back in the day, do the vector stuff. But then I switched to the more fundamental right triangle applications, law of sines, law of cosines, and then save that for some of the others in science courses. You know, I thought that went a lot further, but yeah, This is the very famous what? Resultant vector, meaning the sum vector. Okay. So you can do the same thing, in all honesty, for all these others. Okay. So if I go try to erase some of the work we did because it's in our notes, you can find the magnitude and direction of all of these. And that's typically what they want you to do, like as an exercise. To be honest with you guys, that's typically what they'll do. They say, okay, now that we know you can do vector arithmetic, right? What's the magnitude and direction of those particular vectors now? You just use the formulas I gave you guys yesterday, right? So if we move some of this, okay. Like if I said, what's the magnitude of this vector difference? Now, they don't have a name for the vector difference other than just that vector difference. It's not special like the resultant vector. Okay. So what's the magnitude here? How would you guys go about finding the magnitude? Right? Don't you need that A value? Because I need A. Isn't A here? Well, what's B? Do you guys know? Here's A. Here's B. We need 1 squared plus negative 8 squared. Here's 1. Here's negative 8. 1 squared is 1. What's negative 8 squared? Do you guys know? Is that 64? What's 1 plus 64? 65. So what did you guys just find here? What is this? Do you guys know? That's the what? Magnitude. What does magnitude mean? Length. Okay. Now, what if I say to you guys, okay, well then what's the direction now that you find the magnitude? Well, you say what? Tangent theta is B over A. So that's negative 8 over 1. Is that true? Do you guys remember that? And what's negative 8 over 1? What does that mean? Isn't tangent theta going to be what? Negative 8? So let's move everything here. Theta is what now? Inverse tangent of negative 8. So what does the calculator say? What's inverse tangent of negative 8? We're going to have to go to the calculator. You guys know that? Okay. What is that going to be? You get an error? Where's inverse tangent? Negative 8. Let's make sure we know what we're in degrees, right? Are we in degrees? Yes, we are. What's that going to be? Let's go to the nearest whole number. What's theta? Isn't that negative what? Negative 83 degrees. Is that true? All right. Yeah.
So in this whole equation, before we did magnitude, so we were just finding the magnitude and now we found the length.
Well, the magnitude is the length.
Sorry, magnitude and the direction.
Direction.
That's all we did.
Yeah. Well, we found we found the vector difference, and now we're trying to find the length of the vector and the direction. However, there's going to be a point I want to make here. Is this an accurate description? Because you might have an issue with the angle. Okay, remember, using inverse tangent, we threw out quadrant what? Quadrant 2 and quadrant 4 with inverse. So I want you to understand this in detail. So you might say, why is it so important that I have to graph this? Because this is going to be a small detail that people may what? Have an issue with. Go back. For inverse tangent, to talk about an inverse, didn't you throw out quadrants? The answer is yes. You threw out some quadrants, ladies and gentlemen. You threw out quadrant 2 and quadrant 4. So what that really means is that when you say all students take calculus, tangent is positive in quadrant 1 and tangent is negative in quadrant 4. Is that true? You're looking at the picture. This is why we said all students take calculus. So this solution that they gave you here is really that negative angle. Is that right? Does that make any sense? Yeah. That's what your calculator told you. Now, my question to you is, you know this vector that you guys found that is written 1 comma negative 8? You say, Mr. Judge, why did you graph this stuff yesterday? Why do we have to graph a vector? Because is that vector 1, negative 8 in quadrant 4? What if it was in quadrant 3? Uh-oh. Yeah, let me share with you guys that, right? So is 1, negative 8 in quadrant 4? The answer is what? Yes. So this vector 1 is in fact in quadrant 4. So you're happy about that. But I want you guys to make the following observation here. I'm going to go to this vector right in here. Okay, I'm going to erase this to illustrate to you guys an important detail and an important point. Because as you do some homework and work with some of this stuff, you might say, Mr. Judge, I have a problem. Look at this example now. We can get the magnitude of negative 4w by saying, again, here's my A, here's my B. Negative 4, what's this? Negative 20, right? So I'm going to take negative 4 in parentheses and square that. Negative 20 in parentheses and square that, okay? Yeah, I get 16. Yes, I get 400. I get square root of 416. You go, what do I do with this? Well, what is the square root of 416? Let's get the numerical answer, right? So it's going to be second square root 4, oops, clear that out. second square root 416. What is this? That's approximately 20.4. Okay. What did you just find? That's called the what? The magnitude. What's the magnitude? The length. That's the notation. So this vector is about 20.4. Okay, fine. What about the direction again? You go, okay, tangent theta is negative 20 over negative 4. What's a negative over a negative? Do you guys know? That's 20 over 4. Yes, you can simplify it. It's not really necessary. Oh, isn't that 5? Yeah, it's going to be 5. Good. You can say 20 over 4. Okay. Not to simplify, you can evaluate it. All right. So now theta is the inverse tangent of 5, right? This is my point. I want to make a very important point here. Second, what's the inverse tangent of 5? If I go to the TI, I'm going to the TI now. What's the inverse tangent of 5? What angle is this to a whole angle? Isn't that going to be, how many degrees is that? A whole angle. 78.6 is really what? 79 degrees. Is that true? Okay. All right. So here is a very, very important point I really want to make for you guys here. It's important. Okay, so 79 degrees. Now, you see this vector? What quadrant is this vector in? Where's negative 4? Negative 20. So if you look at this, as I was doing, one, two, three, 4. All students take what? Calculus. You guys okay with that? Why did I cross out quadrant 2 and quadrant 3? Because the second you use inverse tangent, those quadrants are gone. Is that true? So your angle is 79 degrees. All right. What's the real problem, though? What's the problem? Yeah, the vector is in quadrant what? It's in quadrant 3 because they're both negative. So you go, oh, what do I do then? See, your vector is go to the left, negative 4, go down, negative 20, right? Believe me, the vector, though, is in quadrant 4. This is where vector V is. You have an issue here. Or not vector V, whatever vector that we called it. So how do you guys think you fix the situation? Right? Because your calculators, ladies and gentlemen, they don't have all the answers. This is why you can't trust them. They're useful tools, but the answer is that the direction of that vector is not 79 degrees. Is that true? What is the real direction of this vector? You can do this. Isn't that what? Can't you add 180? Right? You add how many? This is the move. You add 180. So your calculator may be helpful in getting the answer, but it certainly is not what? the authority. Your brain is the authority. Your brain, ladies and gentlemen. So the true angle, I should say, the true direction of this vector is really what? 200 and what? 59 degrees. Okay, so I want you guys to know that detail will always happen. If a vector lives in quadrant 2 or quadrant 3, you're going to have that issue. Because you threw out quadrant 2 and quadrant 3. Your calculator is limited. It goes, I only know for inverse tangent, I only know angles from quadrant 1 and quadrant 4. And that's the deal, ladies and gentlemen. Isn't that interesting? So, yeah, all the little details. Your brain is really where you don't want to trust technology. It helps, but it doesn't give you everything. Anyway. Let me look at this here. So I'm going to look at something here. I'll have you guys look at this as I look at this final homework, Let's kind of fix some of this here. Oh, what's going on? Come on. All right. So, what happened here? I can't. That's a little weird. Okay. So, where I'm at right here. Yeah, that's kind of very weird. Can't seem to get into that field. There we are. I don't know. Let's adjust that. We'll have you guys do odds. Find the magnitude and direction. Yeah. All right. So I modified that to reflect exactly what we went through the last few days. You want to plot your vectors. You want to, ladies and gentlemen, find magnitude and direction and do some of the arithmetic there. All right. And that will help you again for your what? Your final exam, okay? You guys know what I'm saying? So that kind of stuff is going to be on your what? Final. The stuff we went over here. Anyway, let's have you